To understand the physics behind the Rubens flame tube, we have to understand the basic concept of the closed-ended pipe. If the pipe is closed-ended at one side and open-ended at the other side, the open-ended side has to end with antinode, and the closed-ended side has to end with node. The definition of node is a point along a standing wave where the wave has minimum amplitude. And the definition of amplitude is where the definition of antinode is where the amplitude is maximum. If we see the length of the pipe is L, one wavelength, which is lambda, is equal to 2 loops, which we call rugby balls in class. Based on this drawing, we can tell the length of the pipe is equal to 1 lambda over 4, and we can say that lambda is equal to 4L, which is the fundamental wavelength. Based on this drawing, we can tell the length of the pipe is equal to 3 lambda over 4, and we can say that lambda is equal to 4L over 3. Based on this drawing, we can tell the length of the pipe is equal to 5 lambda over 4, and we can say that lambda is equal to 4L over 5. If I want to write down any possible wavelength, it's going to be 4L over n, except instead n being any possible integer, the only allowed ones will be the odd ones. So based on this, we can tell that getting an even number of harmonics in closed-ended pipe is impossible. Sound wave, which is created by a loudspeaker at one end of the tube, travels through the tube and reflects back once it hits the closed end of the tube. Now there are two waves, one generated by the speaker and the other one which reflects back. The combination of two waves create a standing wave pattern. The changes in pressure along the tube makes the flames spring up or die down in waves as the frequency is generated by the frequency generator. In this drawing, we can tell that this part is antinode and this part is node. Our aim for this investigation is to check whether the Rubens flame tube is open-ended or closed-ended. Our hypothesis is that the tube is closed-ended.
Firstly, once a standing wave pattern appeared, we will use the equation Fn equal to Nf1 to calculate the fundamental frequency. And as the picture is shown, we set the frequency generator at 190 Hz, and a standing wave pattern of the third harmonic wave appeared. We are able to find the fundamental frequency by dividing 190 Hz by 3, which gives 63.33 Hz. And that is our fundamental frequency. Secondly, we multiply the F1 fundamental frequency with 3, 5, and 7 to create its corresponding standing wave harmonic pattern. And lastly, to confirm that the Rubens flame tube is closed-ended pipe, we multiply the F1 with 2, and if the standing wave pattern disappears, the tube is closed-ended.
316. This is going to fifth.
Okay. Fifth to third.
And discussion. After the investigation, we conclude that the Rubens flame tube is closed-ended, as it can only create standing wave pattern for odd numbers harmonic, like 1, 3, and 5. For closed-ended pipe, there will always be a node at the closed end and an antinode at the open end. There are certain limitations we had faced during the investigation. It was very hard to maintain a standing wave pattern as the speed of the sound keeps changing as the temperature of the particle inside the tube increase, as velocity and temperature has a direct relationship. Since we are fixing the frequency and the speed is increasing, this caused a change in wavelength, which messed up the standing wave pattern. By lowering the amount of gas releasing into the chamber, we were able to get more stable standing wave pattern. For the future investigation, we are suggesting that we should drill more holes at each end of the pipe as the pattern of the standing wave will be more clear.